Hi everyone! In this video we are going to look at an extreme example of a dipole-dipole interaction that is much stronger. It's known as the hydrogen bond. And the hydrogen bond is actually kind of a misnomer. It's not really a bond. It is an intermolecular force. Okay? So it is weaker than an ordinary covalent bond, but the strength of a hydrogen bond is on the order of maybe 10 to 15 kilojoules per mole, whereas a bond has an energy of 100 or more kilojoules per mole. So when exactly do we see hydrogen bonding? Well, let's take a look at this graph that shows the boiling point plotted against the atomic weight. So we know that as atomic weight increases, the dispersion forces increase, and therefore we should see an increase in boiling point. And we do for my group 4 hydrides. When we look at group 5 hydrides, we see that there's an anomaly here. The NH3 example has a significantly higher boiling point than you might expect. When we add in group 6, we see the same thing. Water is anomalously high. And then group 7, again, HF has a higher boiling point than all of the other group 6 hydrogen halides. So how do we explain these anomalies in this trend? Well, that's where the hydrogen bond comes in. Highly electronegative elements like F, O, and N are those that can participate in hydrogen bonding. So we often say hydrogen bonding is fun. Anyway, if we draw out the structure of, say, water, the fact that oxygen is highly electronegative makes this bond dipole pretty significant. And this electropositive hydrogen atom is seeking more electron density, and it can find that electron density on a neighboring or nearby water molecule. So we have the appearance of a dipole-dipole interaction where we have the negative and positive ends of a dipole, but the fact that this hydrogen can get much closer and is much more attracted here makes this more energetically favored and therefore stronger interaction, lower in energy overall. So the hydrogen bond is directional. It is required to have a 180-degree orientation here. Aside from having a hydrogen atom attached to F, O, or N, that's known as my donor, the atom participating in the hydrogen bond, we also need an acceptor to be present. And the acceptor is the component that is accepting that hydrogen by utilizing its lone pair of electrons. We can use hydrogen bonding to explain the fact that water, HF, and ammonia have higher boiling points compared to what you might expect. And hydrogen bonding is not only important in predicting boiling points, but it also is what determines the specificity of base pairing in DNA. You may be familiar with the fact that adenine and thymine prefer to bind with one another, and this is due to the fact that they form 2 hydrogen bonds. Guanine and cytosine, on the other hand, like to pair together where they have 3 hydrogen bonds. And these pair up in a nice way because of the capability of hydrogen bonding between these pairs. Take a look at these compounds and see if you can predict whether or not hydrogen bonding would exist in these structures. Okay. So when we are trying to look for hydrogen bonding, we want to look for F, O, or N atoms that contain a hydrogen, and then we also want to look for possible acceptors, things like F, O, or N that have lone pairs. So looking for the donors first, we look for heteroatoms that have hydrogens attached to them. So this oxygen does not have a hydrogen attached. It will not be a donor. Here we have a donor and another donor. These hydrogen-oxygen bonds could participate in hydrogen bonding. The same for this compound, we have two donors. Here we have nitrogen-hydrogen bonds, and here we have oxygen-hydrogen bonds again. So 4 of my 5 examples have hydrogen bond donors. That's one piece here. Now, let's look for acceptors. So there are lone pairs here. So this oxygen could be an acceptor. There are lone pairs on this oxygen, so this could be an acceptor. Likewise, this one could be an acceptor. Moving on to this one, we have several oxygen atoms, all having lone pairs, so we have quite a few acceptors here. Nitrogen with a lone pair can accept hydrogen bond and oxygen as well. So, as long as we have both a donor and acceptor, hydrogen bonding will exist between molecules. So if we have a pure sample of peroxide, this would hydrogen bond with itself. If we have a pure sample of oxalic acid, this would hydrogen bond with itself. Of methylamine, yes. Of methanol, yes. But if we have acetone here, it doesn't have a donor, so there will not be hydrogen bonding here. So we might be able to predict, as long as these are somewhat similar in terms of molecular weight, that the hydrogen bonding here would lead to higher boiling points. Okay? Now, if we mix acetone with hydrogen peroxide, then the acetone molecules could participate in a hydrogen bond with the peroxide molecules. And that might look something like this, where we have a donor and an acceptor from acetone. So here is my acceptor, and here is my donor. Okay? So the donor and the acceptor will pair up to participate in this hydrogen bond. If you have any questions, please let me know, and thanks for watching.